So let's see. ODP 213, questions on that? Something like that, right? I like for loops. You can use fors, you can use whiles. Usually a for loop is good if you know that you want to do something a certain number of times, right? Particularly if you have a numeric variable and you have a value that you want it to go up to, or up to 1 less than, or something like that, right? A for loop is a very natural structure for that. If you're trying to loop until some condition is true or false, that's usually a while loop. And you can do for loops with a while statement, you can do while loops with a for statement, but it's probably a little confusing to mix those together, right? If you really want to do for I equals 0 to 10, you can do this. Right, and that works perfectly fine, but this is really just saying for I equals 0, I less than or equal to 10, I plus plus. Right, and you're really just putting your initialization right here, your test condition right here, and your increment right there. So if you're doing those three things, right, a for statement puts them all in one spot, right? And that's sort of what people are accustomed to seeing. On the other hand, if you want to say while C is not equal to VOF, right, you can do that as a for statement. Right, and you can throw some initialization in here, and you can throw something like C equals get car at the end, and that works too. It's just not what people are sort of expecting to see when you see a for statement, and so you might get some raised eyebrows on the job or something, but it works perfectly well, right? And if that's the way you think of it, go for it.
So you always default to for loop when you can, basically?
Me or one?
What's that?
Me or one in general?
You specifically.
Me specifically? No, I pretty much only use a for loop if I'm incrementing a variable or decrementing a variable to some limit, like an integer, right? If I'm doing anything else, I use a while loop. All right. So a couple of announcements before we go on to ODP 214. First of all, WSUV advisors will be here on February 21st. If you're transferring in fall and you want to touch base with an advisor from WSU, make sure you've got all your ducks in a row and stuff. They'll be in the collaboratorium. There's a sign-up sheet next to the door. There's still some open spots as of an hour ago when I looked last. But you have to sign up for an appointment. They're fixed time slots. And so that's an opportunity to save you a phone call or a trip up to WSU if you have questions for them. So that's February 21st. Next thing, even though we're halfway through the middle of our 3-quarter sequence, and you're probably making good progress on your SLP. Occasionally, people at this point are thinking, this isn't really what I want to work on for another quarter and a half, or my partner has disappeared, and I don't think I can do this without them. If you're feeling like you want to make a change of gears, okay, if you're working on a project and you're making progress, stick with it. But if you're already at a place where you feel like you're thinking of changing gears, maybe trying a different project, if you're interested in doing an SLP related to Android app development, Izad is looking for somebody to basically develop an Android app that can be used to control the electric car that's sitting in the collaboratorium. It's basically going to interact with an Arduino and pick up mostly sensor information, speed and power level and things like that, and display it on a console. And so if you want to learn Android app development, that's sort of a handy problem to use as a development target. So if you think you're interested in that, you can talk to Izad, get some details on it, and if you want to go that way, talk to me, and we'll figure out how to switch your SLP over. So I just wanted to toss that out there. But if you're happy where you are on your SLP and you're making progress, stick with it, because it is kind of late to be starting something new. All right, so today's ODP, so it's another hash function, but this time it's a hash function that supports probing, meaning that it takes two arguments. The first argument is the string that you're hashing. The second argument is an integer. And even if you have no idea what probing means, you can still do this assignment, okay? So the hash function is basically add up the ASCII codes for each character in the string, then add the square of that integer argument, which we call the probe, and reduce mod 31. So hello, in yesterday's ODP, hashed to a value of 4. It's still going to hash to a value of 4 right now, if your second argument, your probe, is equal to 0. If your second argument is 1, you add up all the ASCII codes, you add 1 squared, which is 1, you reduce mod 31. Your total final value should go up by exactly 1. If you hash hello with a second argument of 2, you're going to add up all the values, mod 31, which gives you 4, and then you're going to add 2 squared, which is 4. 4 and 4 is 8. That's your value. 4 and 9 is 13. If you put in a probe of 10, your final value will be 104. Mod 31, which turns out to be equal to 11. So it's almost exactly the same code. You just write your function to take a second argument, which is an int, add the square of that integer to your final sum, reduce mod 31, and return that. So it should be small changes on ODP 213. And the way to square an integer in C is just p times p. So if you do caret is an exclusive OR operator. So some languages that's an exponent. In C it's not. If you do p star star 2, I think you get a syntax error. And if you play around with the pow function, which is used for raising things to a power, that expects doubles or floats as arguments, so you need to start doing some casting, and doubles and floats are imprecise anyway. It's your easiest bet, right? Be lazy. P times P gets you a square. On 213, just something I wanted to point out. If your string is really long, if your string is like 1 billion characters long, and you add up all of the ASCII codes, you can get into an overflow. Right? ASCII codes can be around 100, so if you're adding up 40 billion characters, that'll get you to 4 billion. That's going to overflow your integer sum. An easy way to avoid that is every time that you increment your sum, reduce mod 31. Right? Because 215, we haven't done it yet this quarter, but if you took a previous quarter, if you add 3 things together and calculate what that sum is, mod 31, you get exactly the same as if you do A mod 31 plus B mod 31 plus C mod 31, which is exactly the same thing as adding A and B together, mod 31 plus C. All right, you can take these reductions modulo whatever anywhere that you want, right? Whether you're adding or subtracting or multiplying, and you'll end up in the same place. But by reducing mod 31, every time that I increment my sum inside my for loop, my sum is never going to be bigger than 30. It's always between 0 and 30. Doesn't matter how many things I add. Right? This is what we do with pencil and paper when we're trying to do large calculations, like trying to do a public key encryption on paper. By constantly reducing modulo whatever moduli we're working in, keep our numbers small. Right? So we can do these big exponential calculations. We never have to work with a number, in this case, bigger than 30. So that's just something to mention. All right, questions on PA3 so far? And I got PA2 graded, by the way. I gotta post the grades and comments in Canvas, but I got everything graded this morning finally, and they look really good. Okay. Biggest issue, other than freeing memory, which is always a little tricky, was delete sometimes. People were having issues with delete. But as far as using arrows to dereference pointers and access memory and using mallocs and that kind of stuff, everything looks perfect. So we're in good shape right now. But I'll get those posted up this afternoon. All right, let me talk about some more coding for PA3. And then I want to talk about other versions of hashing. I want to talk about hashing with probing instead of chaining. So where we're using this probe to search different spots in a hash table, I want to go through the details of that a bit. But for now, let's look at PA3 some more and figure out how we use linked lists to build out our hash table entries. So we were looking at these yesterday, and we talked about hash init is just a loop that calls list init however many times hash size says. We looked at hash add, we looked at hash find, right? Hash load is supposed to print the load in each cell, so it's supposed to print out something like this. Right, so entry number colon length equals this, entry number colon length equals that. And that's just a for loop, right? For I equals 0 to hash size minus 1, print out entry index colon, and then print out the length of the list at hash table bracket I, and you get that by calling list length. All right, so that's just a for loop calling your length function. Hash dump prints the contents of a cell. That's just calling your list print function. And in your main program, if the person types in the command star dump without specifying a cell, just call hash dump for cell num going from 0 to hash size minus 1. Right, so put the pieces together. And hash free, just go through hash table, call list free on each of the nodes in there, and then free the hash table itself. So let's look at the list functions. And our node is a little different. So it's got 3 data fields, which I just called first. So list init is creating a new node, right? Create an empty list, which is a sentinel node. So malloc size of struct node, which will be bigger than your node from PA2, and set the next field equal to null. And if you do your list correctly, you're never going to look at the plate first or last fields inside the sentinel node, so you don't need to initialize those. If you don't initialize them and you run valgrind and valgrind starts reporting about uninitialized values, it may be that you're doing something with those values. That's a good check. Okay, but sentinel node, you never have to look at or touch the data fields. The only thing you use with the sentinel node is the next field. If it's null, your list is empty. Otherwise, null or next points to your first data node. So init is pretty much like what we've been doing. Just do a malloc, set next to null, return the address of that node that you malloced. Okay, list add starts to get more interesting. So list add, it's a void. Takes a pointer to a struct node, so that's a sentinel node. Takes a string, which is the plate, first name, and the last name. And I want you to insert new nodes at the beginning of the list. Okay, don't alphabetize, don't search for the right place, don't insert at the end. Just insert a new node right at the beginning. So what do we do? Make yourself a temporary node pointer. Malloc enough space for a struct node. Okay, again, not a struct node star, but an actual struct node. So size of struct node. So temp is now something like this. Okay, with uninitialized values in each of those fields. Sent, which is the thing that we pass to our function, is something that looks like this. And your goal is to put temp right here in between the first two nodes, the sentinel and the first data node. So set temp equal to malloc. Okay, that gives us a chunk of memory. If we set temp next equal to sent next, right, that causes temp to point wherever sentinel is pointing. So our new node is pointing to what was the first node of the list. And then sent next equals temp. So you've done this before, you've done it in more complex situations. This is just adding your new node into the beginning of the chain. So sentinel points to my new node points to the old first node, points to the old second, and so on. Alright, so that you've done, that code is pretty much verbatim from PA2. The trickier part is setting up these data fields. So if our data was just an integer, we could just say temp arrow data equals whatever data you passed in that you wanted to store. But we're passing in strings, okay? Car star P, that's an array of characters. It's a string. It's presumably a string that ends with a null terminator, which means we can use things like string copy to copy from here into whatever destination we want. So string copy comes from string.h, right? And this is kind of a oddball function. The first argument is the destination, the second argument is the source. So we'll copy from whatever that second argument is pointing to into whatever the first argument is pointing to. And it says in underlines, beware of buffer overruns. Okay, this is a good exploit capability, good exploit option. Because it doesn't do any checking to see if there's enough space in the destination. It just starts copying from here to there and incrementing the pointers until it finds a null terminator. It copies the null terminator and then it exits. Right? But how does it know if there's enough space in des to safely copy everything that it wants to copy? There's no way for it to know. Because arrays in C don't have a notion of length. The way it knows if it's safe is it keeps copying, and if it gets a seg fault, it knows it wasn't safe. But if it inadvertently steps on another variable like I, or buffer, or password flag, right, it has no way of knowing that that's what just happened. So that can be a concern, but for us, it's a definite issue. Because how much space do we safely have inside this plate array? Right, so we malloc a new struct node, we call that temp. This thing right here is a car star. It's pointing to some location in memory. How many characters can we safely write starting at that location? Can we write 10 characters? Can we write 100 characters? Can we write 1 character? Should we try it? Let's just play around. All right, so we've got a struct node pointer. We'll malloc a chunk of space for it. That's all good. We can set the next field to be null. That's fine. Let's go ahead and load some values into the fields.
Will that just say full?
It will.
Because the address is still 0.
Whoa, if I get that far. Man, it should be able to read my mind by now. There we go. So we run it, seg fault, right? So let's see what's happening here. Temp is initially null, right? Size of struct node is 32, so this call to malloc should get us 32 bytes. Let's go ahead and execute that. Temp is no longer null. Temp is some location in memory. That's a good looking memory address. And if we examine that location, right, just got some stuff in there. I'm going to set temp next equal to null. Okay, so let's see what temp is pointing to. It's pointing to a struct node. And it'll show me the value of plate first, last, and next. They're all equal to 0. So I'm about to say copy into temp arrow plate ABC1, 1, 2, 3. Temp arrow plate is 0. It's null. We're trying to copy this string into memory address 0. That's a classic seg fault. We can't access memory address 0. Similarly, if I tried to print out what temp arrow plate was pointing at, right, can't access memory address 0. So temp arrow plate is 0. The thing at the place that temp arrow plate is pointing to is inaccessible. So I could give it some weird location. Oh. Right, and now temp arrow plate is pointing somewhere, but that's because I gave it an address. Well, I gave it a random address that'll probably like cause the universe to collapse if I execute this. But we can find a good address to point it to by using malloc, right? Go ahead and run it. Hey, it worked. All right, so we're going to copy ABC 1, 2, 3, and that's going to seg fault. So make space for copying in plate. So temp arrow plate is 0. We want it to point to a block of memory where we can store ABC 1, 2, 3. That's what malloc does for us. Okay. How many bytes do we need? Well, it depends on what we're trying to store there. Don't just allocate 32 bytes or 1,000 bytes or something like that. Allocate exactly enough bytes to do what you want to do and no more, but definitely no fewer. Okay. So I want to copy ABC 1, 2, 3. I can count that, that's 7 characters, but I don't have to count. I can say string length of, and typically this would be a variable instead of a string inside quotes.
And a +1, correct?
And you gotta add one more because since the string length of this is going to be 7, we actually need 8 bytes to store the string because we always have to store a null terminator at the end. And wow, that's one of those bugs that will drive you nuts. Because malloc always gives us chunks that are 16 or 32 bytes. And if we forget to add +1 to the malloc, we're usually okay. I need 8 bytes, I'm asking for 7, it's gonna give me 32. I got space for that null terminator anyway. Until I try to store a string whose length is 32. Because then if I ask for malloc 32 bytes, I get exactly 32. If I'd asked for 33, I would have gotten 48. So if my string happens to be 32 characters long, I don't have space for the null terminator, and that's where I suddenly get a seg fault. And you got your program, you were working on it for a week and a half, it's working great, it's working great. You're ready to turn it in, you do one final test, and bam, it suddenly blows up. And it's because you had a first name somewhere that was 32 characters long. Right? right? That'll drive you crazy. All right, so that allocates space for template, and then we can go ahead and do this copy. So temp arrow plate is null right now. Once we do the malloc, temp arrow plate is another good memory location, pretty close to the one I guessed before. Right now temp looks like this. If I go ahead and I do that string copy, now plate looks like this. Temp looks like this. The plate field is ABC 1, 2, 3, and first, last, and next are still 0. All right, so that's the only other trick in dealing with this new type of struct node, is before you can string copy your data into the different fields, you need to malloc space. And this also means when you're freeing things at the end, you need to free those. Okay, that's not hard. Before you free temp, just free temp arrow plate, temp arrow first, temp arrow next, and then free temp. Okay, but this will really exercise your understanding of what's going on with these pointers and what do they actually refer to in memory. And don't just blindly say free temp arrow plate, right? Think about why you're doing that. What is temp arrow plate? Is it a string? Is it a location in memory? Is it a pointer? Well, yeah, it's all of those things, right? So try to make sense out of that. All right, so your add function is basically the same with just these changes. So malloc space for it, set the next field, and the sentinel points to the new node that squeezes it in, and then do 3 mallocs and string copies to make space for and copy in your arguments plate first and last into the plate first and last fields of your node. And you're done, you've got it added to your list. All right, so list find. All right, to pass as a sentinel, a plate, a first, and a last. We're searching for the license plate. Okay, that's the key that we're searching on. So we're looking through the linked list for a node where the license plate matches this argument P. If we find it, then we want to take the first and last name from that node and copy them to F and L. Okay, so we're only searching on P. That's the key for our search. So I can start off with a struct node pointer equal to whatever the sentinel is pointing to. So this is my first node, or it's null. So while we're not out of nodes, right? So is temp the node we want? So right, so string compare. So it comes from string.h, takes 2 strings, compares them, and and returns 0 if they're the same, non-zero if they're different. So what are we comparing? We're comparing the plate stored in temp with the argument that we passed into the function. All right, if string comp returns 0, then and only then we know that plates are the same. And so we want to take the plate from the node and copy its first name field into this argument. Take the last name field, copy into that. Just another string copy. And the assumption that we can make here is that when somebody called this function, they gave us in this field f the address of a chunk of memory that's big enough to hold the first name. So we don't want a malloc f here. If we set f equal to malloc something and then we string copy, we're copying into a block of memory we just allocated. Has nothing to do with the f that was passed to us. And when the caller gets back from this function, f is unchanged. So we absolutely want to copy into that argument. It's a little dangerous though, because we don't know how big that array is. Right, so I think I tried to take care of that. Did I give you a maximum size? I didn't give you a maximum size. Oh, that's a bummer. All right, let's see. So license plates, first names, last names, never more than 32 characters. Okay, but don't hardwire them in your struct node. Okay, I think this is why I didn't put it in the assignment. Don't just make your struct node a character of 32 for plate, a character of 32 for first name, and so on. Allocate those dynamically. But in order to write this program, right, what happens if the database file that you read has a first name that's 10 billion characters long, right? You need to know that when you set up your variables that you're going to pass to list find and functions like that. So in your main program, right, you can assume that these things are never more than 32 characters. So you can just pick a reasonable sized array. All right, so copy from the field in the node into the argument that was passed to you. Do the same thing for the last and then return 1. Right? Otherwise, just move down the list. And if you get out of your while loop, it means you move down past the last node to the following node, which was null. That's where you just return 0, which says nothing is, that no node in there has that plate, and we haven't changed first or last in that case. All right, so list add, list find. List len is just go through your list, count up how many nodes you have. So set a counter equal to 0, start it off with some temporary equal to where the sentinel's pointing. Well, temp is not equal to null. Increment your counter, temp equals temp next. When you're done, just return your counter. Now, worst case with that, you get off by 1 because you return too soon, or you started at the wrong value, or you're incremented in the wrong place, or something like that. So just test that with your lists. List print, exactly the same as the print that you've had before, but instead of printing your data with a %D, you print your plate, your first and your last with a %S. And make sure you do it in the format that's described up here. So plate, angle, bracket, plate, name, colon, last name, comma, first. Okay, but it's just 3% S's. And then list free, as we said before, basically it's the same thing you were doing before. Start off with the sentinel, move to the next node, but remember the previous node. Once you're at the next node, right, you want to free the previous node, but you have to free the plate first and last names also. So free previous arrow plate, previous arrow first, previous arrow last, and then free previous. And when you get past the last node where your current node is null, you're done. You can just return. All right, questions about any of that? That's kind of all I have for suggestions for PA3. All right, so I want to talk some more about hashing. I want to talk about hashing with probing and go through some of the issues with that. Tomorrow I want to go through PA2 code, just show you some ways to do that and talk about specifics from what I saw in grading. Friday is our midterm. Thursday we'll talk about something else. We might start talking about trees. Or stacks and queues. We got to do stacks and queues too. We'll probably talk about different data structures on Thursday. But let's talk more about hashing. So we start with the same setup as we've been dealing with an array. Let's just suppose it's an array with 100 entries in it. And we have a hash function which returns an int. And so theoretically, we take our first string we want to store, we hash it to an integer, we store it at that location in the hash table. And that works fine until we start storing too much stuff in our table. And it's not that the hash table is filled up, but it's that we found multiple things that hash to the same location. Okay, so that's what we call a collision. In the case of chaining for PA3, that's not a problem, because anything that hashes to this location just gets added to that linked list. And we can put things into our hash table forever. Okay? That's not the case with probing. So probing, we want to actually store all of our data in this hash table. Because if you're storing your data in a list that's pointed to from these hash entries, as that list grows, your search time, your storage time decreases, your search time decreases. And if you're trying to delete and you have to search the list for a node to delete, that starts to decrease in performance as well. So probing, we store everything in the hash table. We've still got a nice efficiency, theoretically. So, basic idea of probing. So hash your key to an index. If index is available, store it there and you're done. If a collision, rehash your key to a new index, and then go back to step 2. So we keep rehashing your keys to different indices and checking to see if that index is available. Okay, so how do we implement that? Start off with an integer equal to 0, typically. And our hash function is ODP 214. It takes 2 arguments, this key and a integer. And we store that in an index. If we have a collision, increment the probe and go back up here. So that's our rehash mechanism. Right, call our hash function with an increasing second argument, and that should give us a different location, a different index in which to store that key. And we just keep doing this until hopefully we find a place that we can store it. But there's some details. One of them being, how do we know if this entry in the hash table is already in use? Right? With chaining, we know this is a sentinel node, and we just insert after the sentinel node. It doesn't matter if there's any data stored there or not. With probing, we've got to know if we've got a collision, which means we need to have some way to detect, have we already stored something in this location? Because there's always something there, but is it something that we put in and we want to preserve, or is it just junk that was there when we ran our program? So how do we tell if a spot is in use? And then searching and deleting get more complex. So we touched on some of this the other day, but we'll spell out some more details of this tomorrow or Thursday. All right, I will see you tomorrow then. Have a good afternoon.